Hello everyone, welcome to the next lecture on the PY question series. Today I will explain you how you can solve the problems related to the group theory. Myself Dr. Harish Garg, you can follow me on my YouTube channel. The channel name is Dr. Harish Garg, you can find it. And in this channel name you can find the playlist of the CSIR UGC net. And you can see the various PY question series lecture available in this playlist. All these lectures are explained with the help of the shortcut tricks. Make sure, because today I will cover about the group theory, you have to watch the number theory lecture firstly, because I use the same concept as I define in the number theory lecture. Now, first of all, I will give you some tips how you can solve this question so that you can get your answer again with the help of the 10 to 15 second time period. Make sure you have to subscribe my YouTube channel and support my videos by liking and comment on the video. Now, the first thing come in your mind whenever you have to think about the group homomorphism. What is the nature of the G? G may be the infinite group, G may be the finite group, G may be the cyclic group, or it may be abelian, any of the nature. Similarly, you can identify the nature of this G dash. Again, it may be the infinite group, it may be the finite group, and so on. Then the first question arises is how you can find the number of the group homomorphism from G to G dash. The one way is you can define the map f of G is equal to say G dash, where G belongs to the G the element of the G and G dash is the element of the G dash. But if you think about it, you can define a map and check about the properties, how many homomorphisms, you can define the kernel, how many kernels, and so on. But that will take a lot of time. But you are unable to get your answer in the 10 seconds. So right now, my objective in this video is to help you. You can solve this problem within the 10 seconds. The first question arises is how you can find the number of the group homomorphism. I will consider case 1 when I consider both is my finite group. Fine. Then after that I will consider G is my infinite, G dash is my finite, both are my infinite, and many more. So the first case, can you identify that if I define the mapping say f from Z2 to Z3, or I can define the mapping from Z3 to Z2, how many homomorphisms, group homomorphisms involved in this function? How you can define that? A very simple approach I will tell you. Whenever you have defined the group homomorphism from Zm to Zn, make sure these are my finite groups. Fine. Then you can simply write as a GCD of m and n. Similarly, here you can see this Z is my infinite group. Fine. This Z is my infinite group and Z of m is my finite group. And I think all of you know that what is the meaning of the Zm. The order of the Zm is m. Fine. Then how you can define the number of the homomorphisms? Group homomorphism from infinite group to the Zm. It is defined as m. Make sure this is the result valid only for the Zm. Similarly, so you can see that once you know, can you define how many group homomorphism from Z2 to Z4? What is the GCD of that 2 and 4? 2. The answer is 2. I hope you can see this is the face when you listen about this video. How many group homomorphism from the Zm to Zn cross Zk? So that is again GCD of Zm, Zn and Zm and Zk. That is a GCD of m and n, while the GCD of m and k. Similarly, you can define the group homomorphism for the fourth case. That is a GCD of mk, m and k, and GCD of n into k. And similarly, for the last case, you can define the group homomorphism as m into k, n into l, m into l, and n into k. All are these possible cases. For example, if now you can see, we all know the order of the S3 is 6, which is again a finite. Fine. And the order of the Zm is my m. which is also finite. Clear? In the previous cases, all these group are my finite order. But make sure this concept, that is a GCD, is applicable only when you define the mapping from Zm to Zn. Fine, not from the any finite group to finite group. Now in this case, since this S appears not the Z, so you can't say this will be the GCD of n comma n. Fine. So in that case, how you can define the number of the group homomorphisms from Sn to Zm, while n must be greater than equal to 3 and n is not equal to 4. So the number of the group homomorphism is either 1 or 2, depending upon that whether m is my odd number or even number. For example, look at that. How many group homomorphism from S7 to S8? Because 8 is my even number, so the number of the group homomorphism is my 2. Similarly, if I define 101 to Z of 91, because 91 is my odd number, so the group homomorphism is 1. So you can see within the 10 seconds you can get your answers. Let me solve you the PY question also. I hope you can like and comment on this video. The first question appears in the June 2016. The number of the group homomorphism from Z10 to Z20. So what is the right answer? GCD of 10, 20. So what is the GCD of the 10, 20? 10 is the right answer of this problem. Look at the next example. The number of the group homomorphism from S3 to, what is that? This is the additive group. This is also called as Z6. Fine. Now since it is not the Z3, so it is not in the form of GCD. So what you can say, since 6 is my even number, so the right answer is 2 is my correct answer. Remember that 2 if m is my even, and 1 if m is my odd. Fine, this is my Zm. So since 6 is my even number, so the right answer is my 2 is the group homomorphism from S3 to Z6. Again, you can see it's a December 2013 number of the group homomorphism from S3 to Z6. Again, you can see this is my even number, so the group homomorphisms are my 2 is the right answer. How many seconds you are needed to solve these three questions? Again, how many group homomorphisms from Z4 to Z6, Z8? GCD of 4 and 8. The right answer is 4 is the correct answer. How many homomorphisms are there? So you can see the GCD of 2 and 8 multiply GCD of 4 and 8. So what is the GCD of 2 and 8? GCD is my 2. GCD of 4 and 8 is 4. So the right answer is 8 is my correct answer. You can see how many seconds you are needed to solve the problem. Maximum 10 seconds you are needed to solve the problem. I hope you can like and comment on this video too. How many group homomorphisms from the Z10 to Z25? Again, it's a GCD of 10 and 25. So the answer is 5. So the right answer of this problem is 5 is the correct answer. How many homomorphisms are from Z2? That's a GCD of 2 and 8 multiply GCD of 2 and 16 multiply GCD of 4 and 8 and GCD of 4 and 16. So what is the GCD of the 2 and 8? 2. GCD of 2 and 16? 2. GCD of 4 and 8? 4. This is also 4. So that is 4, 16, 64 is the right answer of this problem. If you are new to my YouTube video, you can scan and join my WhatsApp group as well. Look at the third case. How many group homomorphisms are there? You can find the GCD of 10, 2 and find the GCD of 10, 3. So the GCD is my 2, GCD is my 1. So the right answer of this problem is how many homomorphisms of this group is 2 is the right answer. Look at this one. How many homomorphism from this? You can see this is my infinite group. Fine. This is my finite group. And what is the shortcut tricks? As I told you, whenever the f is from z to zm, how many homomorphisms are there? Homomorphisms are m. So in this case, m is my 4. So the right answer is 4 is the correct answer. You can see a very simple approach I have told you. You can solve the answer within a 10 seconds. Now you can see it's a GATE 2013. How many group homomorphisms from Z3 to Z9? It's a 3 comma. What is the GCD of the 3 comma 9? 3 is the right answer. Make sure student, I again tell you, you can find the GCD only when it is from Zm to Zn. If it is instead of the Z, it is my say K4, or you can say the D4, or you can say An or Sn. You are unable to find this method. I will tell you also in this video how you can find the number of the group homomorphisms from K4 to say Zm. How you can find the group homomorphism from Z4 to Sn and so on. Let G is the group which satisfies the property. F is defined from the G to 2 to 1 is a homomorphism. It is already given that it is my group homomorphism, such that then the possible group of this. Now since it is already given that it is a group homomorphisms, then which of the following case will satisfy? So I call this is my Z of M. Fine. Look at the options. It is one of the Zm. Now what is the definition of the group homomorphism? It is GCD of M comma 2 to 1. Now it is given that G is a satisfied implies f of G is my 0. That means there is only one group homomorphism. Fine. Because it is 0 for all the G. That is a only one group homomorphism. So can you define that which of the following will satisfy? What is the GCD of 21 and 221? I can factorize them. 21 is 3 into 7 and 3 is not the factor of 3 doesn't divide 2 to 1, 7 does not divide 2 to 1. So that means the GCD is 1. Look at the 51. 51 is my 3 into 17 and 3 doesn't divide 2 to 1, but 17 divides 2 to 1. You can see 2 to 1 I can divide them. 17 is 51. 17 3 into 51. So that means the GCD is not 1. Similarly 71 91. 91 can be factorized as 7 into 13. So 7 is there 7 is a factor? Yes, because 7 divides 2 to 7 doesn't divide 2 to 1. Is the 13 divides 2 to 1? So you can see 13 into 1 13. So that's a 91. 13 into 7 is 91. So this is again not the factor. Similarly 119 is also the GCD. The GCD of the 119 and 221 is not 1. You can factorize them. Again you can see it is divisible by 17 or 9. So the right answer of this problem is A is my right answer. The total number of the homomorphism from this. Now you can see this is not Z. So that means you are unable to define the GCD of something comma 6. Fine. How you can define the group homomorphism? First of all, you can find the order of GLN F of P. Fine. That is a generalized group of matrix. So what is the answer of this? You can define this is P of n minus 1. Then P of n minus P. Then P of n minus P square and so on. How many times you have written? This is n. So you have to return n number of times. Fine. So let me firstly find what is the group. What is the group of order? This quantity. Fine. In this case, n is my 2, p is my 2. So what is the answer of this? P raised to power n. How many times you have written? 2 times. That is n is my 2. So 1 and 2. Fine. So what is the answer of this? 4 minus 1 3. 4 minus 2 is 6. Fine. So therefore, I can write this number is SL6. 6 means 3 factorial. I can write this number is Z6. Now, once it is a S3 and this number is my even. So what is the answer of this? Group homomorphisms are my 2 is the right answer of this problem. Now look at the next one. If F is Z20 to Z10, how many onto homomorphism? They are not talking about the simple homomorphism. If this condition is not given to you, for example, this is not given to you, then how many homomorphisms are there? You can find the GCD of 20 and 10. That is a 10 answer, but you can see none of the answer is there because they are talking about the group homomorphism. So what is the shortcut tricks for the group homomorphism? So let me tell you again. I will tell you based on this G whether this is my infinite, whether this is my finite, whether this is my abelian, whether this is my cyclic and so on. So case 1. Case 1, I assume G is my infinite group. Fine. And G dash is my finite group. The case 1 is my this case. Case 2 when both are infinite. Case 3 when both are finite. The case 1 is when G is my infinite group. G dash is my finite group. If it is a finite group, I assume the order is my n. Then how you can define the number of the onto homomorphism, how you can define the number of the 1-1 homomorphisms, and how you can define the number of homomorphisms. First of all, if G is my infinite group, I can assume this number also, and this is my finite group. Then how you can define the number of the onto homomorphisms? You can define firstly if G dash is my cyclic. Fine. Then there are the two choices. If G dash is my cyclic or G dash is not cyclic. Fine. So if it is a cyclic, then the number of the onto homomorphism is phi of n, where phi is called as Euler function. How you can define the Euler function? You can watch about my PY question on the number theory. I have defined how you can calculate the phi of n. How many 1-1 homomorphisms? Is 0. And because you can remember that what is the shortcut tricks, as I told you, because this is my infinite, so this satisfied, this is my finite, so how many group homomorphisms? Group homomorphism is my m, so you can see this is my n because the order is my m. These are first shortcut tricks. Second case, when both are my infinite group, that means like Z to Z, both are my infinite group. Then how many onto homomorphisms? How many 1-1 homomorphisms? How many homomorphisms are there? The 1-1 and onto 1-1 and homomorphisms are infinite if G dash is my cyclic, otherwise 0. Fine. If G dash is not cyclic, then it's a 0. How many onto homomorphisms? That again depend upon G dash, whether it's a G dash is cyclic or not. If it is a cyclic, then the group homomorphism is 2, otherwise 0. Make sure if G dash is my infinite and cyclic, then the onto homomorphisms are 2. If G dash is my finite and cyclic, then the homomorphisms are phi of n. Third case, when both are my finite, that means if G and G dash are my finite group and finite is of the particular nature Zm to Zn. Can you define the number of the homomorphisms? Homomorphism is GCD of m and n, that I defined that. How many onto homomorphisms? How many 1-1 homomorphisms? Onto homomorphisms are phi n if this n divides m, otherwise 0. Similarly, how many 1-1 homomorphism? That's a reverse case. Phi of m if m divides n, then the number of the 1-1 homomorphism is phi of m, otherwise 0. Now based on these shortcut tricks, you can see my function is Z20 to Z10. Both are my finite groups. Now onto homomorphism, that is 10. Is it satisfied? Yes. 10 divides. So onto homomorphisms are phi of 10. You can see n divides m, so the group onto homomorphisms are phi of n. So what is the phi of n? You can divide them, you can partition into the prime numbers. So 2 into 5, 1 minus 1 over 2 and 1 minus 1 over 5. So 10 into half into 4 over 5. So the right answer of this problem is 4 is the correct. Fine. If somebody will ask you how many 1-1 homomorphisms, can you find the number of the 1-1 homomorphisms? So for the 1-1 homomorphism, this quantity must satisfy. Is it divide? No. 20 doesn't divide 10. So how many 1-1 homomorphisms? 0 is the right answer. Look at this next one. How many onto homomorphisms from Z8 to Z4? So clearly say 4 divides n, 8. Yes. So the number of the onto homomorphisms are phi of n. And phi of n I can written as a 2 square. So the answer is 2. Also remember, as I told you in my number theory, phi of n is n over 2 if your n will be my 2 raised to power k, where k is greater than 0. You can see I can written 4 is my 2 raised to power 2. So I can write directly is n by 2. Similarly, what is the phi of 8? 8 I can written as 2 raised to power 2. So it will be 8 over 2, that's 4. How many group onto homomorphisms from Z200 to Z100? So again, you can see 100 divides the 200. Yes, it's satisfied. So the group onto homomorphisms is phi of 100. Phi of 100 I can written as 4 into 25. Fine. So I can break them. This is the 4. 4 is my n by 2. Fine. It's a 2. It's a 25. 25 I can written as 1 minus 1 over p. So it's a 2 into 25 into 4 over 5. So 5 will be cancelled out. It's a 40 is the right answer of this problem. Look at this and next one. How many onto homomorphism from 2016 to 2017? Now clearly say 2017 doesn't divide 2016. So therefore there is no onto homomorphism. So that means 0 is the right answer of this problem. Moreover, you all knows that if f is the mapping from A to B, then how you can say it's a 1-1? This function is said to be 1-1 if cardinality of A is less than of the cardinality of B, and it is the onto if cardinality of A is greater than or equal to cardinality of B. Now you can see what is the order of the Z raised to power. Z is 2016. This, is it a greater than of 2017? No. So that means there is a no onto function. But I always suggested you can use this concept. That's easy for you to check that. How many group homomorphisms from 2023 to 2024? That's the onto. So clearly say 2024 doesn't divide 2023. So there is no onto homomorphism. Fine. Similarly, you can see the order of this is 2013, which is not greater than of 2024. Now, up to the isomorphisms, number of the abelian group. Now they are not talking about the homomorphism. Up to here, we are talking about the homomorphism. Now the next concept is how you can check about the up to isomorphisms and number of the abelian groups. Very easy. Whenever you are talking about the number, you always write in the prime factorization. So that will be 2 into 54. This 54 I can again as a 2 into 27. That means 2 raised to power 2, 3 raised to power 3. Fine. Then what is the shortcut trick? How you can find the number of the abelian groups? Whenever you have defined the order of G as prime raised to power case, like this case, 2 and 3 are primes and powers are my integers. Then how you can define the number of the abelian groups up to the isomorphism? That's the most important word. That how you can define? You can find the partitions of this ki. Partition of the k1, partition of k2. That means you can define the partitions of the k. You can define as a d or p, where d is my partition of k1, d of k2 is the partition of k2. Now look at this example again. I have written 108 is 2 raised to power 2, 3 raised to power 2, 3. Fine. Now you can see what is the partition of 2, or I can call as a d. What is the partition of the 2? What is the meaning of the partition? How you can write as a 2? I can write as a 1 plus 1. So how many partitions? 2 partitions. How you can write the partitions of the 3? So I can write the 3 as a 3, then 2 plus 1, and then 1 plus 1 plus 1. Make sure ordering doesn't matter. You can't say that 1, 2, 3, 4 because they have the same meaning. So you have to partition is 3 partitions. So this is 3. So the right answer is 2 into 3, 6 is my right answer of this problem. Whatever is the power of there, you have to write the partitions. Look at that, number of the commutative. What is the meaning of this commutative? Is again abelian. Fine. So you have to find the number of the abelian groups up to the isomorphism. So what is the, you can firstly find the partitions. 8 I can written as a 2 raised to power 3. So there is only 1. So what is the partition of the 3? It is 3. So the right answer of this problem is C is the correct answer. You can see up to how many example I have solved, how many seconds you are needed to solve the problem. 10 seconds. I hope you can see, you can like and comment on my this video as well. How many distinct abelian groups of order up to the isomorphism? I can write the 12 as 4 into 3. Fine. So the partition of the 2 will be 2. Partition of 1 is my 1. So what is the product of this? 2 into 1 is my 2 is the right answer. Make sure I have denoted D as my partitions. Fine. The number of the distinct commutative group, that is a abelian group, and it is also given as up to the isomorphism. So I can write the 15 is 3 raised to power 1, 5 raised to power 1. So what is the partition of the 1? 1. Partition of 1 is also 1. So the right answer of this is, you can multiply them, it will be 1 is the right answer of this problem. How many distinct commutative? Again, it's an abelian group of 72. 72 means 9 into 8. 9 I can written as a 3 raised to power 2. It is a 2 raised to power 3. Now they are the prime numbers. What is the partition of the 2? They are the 2 partitions. You can see 2 and 1 plus 1. What is the partition of the 3? Partition of the 3 is my 3 because 3, 2 plus 1, 1 plus 1 plus 1. So there are the 3 partitions. So the total partitions are 2 into 3, that is my 6. So number of the abelian groups are my 6 is the right answer. Now, this is the shortcut tricks. As I told you, if you have the mapping from the Sn to Zm, then the number of the group homomorphisms are 1 and 2 if it is odd and even. Another shortcut tricks. As I mentioned you, if you have the mapping from Z to Zm, how many group homomorphisms? This is my infinite group. This is my finite group. Fine. How many group homomorphisms are there? That is a M. But if you look at the converse, F, this is my finite group. Fine. This is my infinite group. Then how many group homomorphisms? This is, remember, we are talking about the group. Then it's a group homomorphisms is my trivial homomorphism. That's the one only. Moreover, it's instead of the Zm, if I write as a G, where G is any finite group, then the homomorphism is 1. Where G is any finite group. That means if I say S3, the order of the S3 is my 6, which is finite. Fine. So you can see S3 to Z, which is, what is the group homomorphism? 1. So that is the right answer. Now, If you have the alternating group A4 and how many group homomorphism from A4 to the Zn, it is a 1 if 3 doesn't divide n and 3 if 3 divides n. For example, if you write A4 to Z3, how many group homomorphisms? Because they are not from the Z4, so that means you are unable to define the GCD. They are not from the Sn, you can't say it's a even and odd. So but you can see 3 divides 3, so the group homomorphisms are my 3. If you define the Z4 to Z7 for example, then 7 does not divide 3, sorry, 3 doesn't divide 7, fine. So then the how many group homomorphisms? 3 doesn't divide 7, the group homomorphisms are 1. If you have the defined as a Kelvin group and the quaternion group Q4, Q8 or K7, if you define the mapping from the K4 to Z7 or Q8 to Z7, then how many group homomorphisms obtained? You can write it directly as 1 and 4 if n is my odd, n is my even. Make sure if you have the Sn to Zm where n is my greater than 3, n is not equal to 4, then how many group homomorphisms? 1 and 2 if m is my odd and m is my even. Similarly, if you have the Q8 and K4, then if it is a odd, that is a n is my odd, then it's a 1. If it is even, then it will be my 4. If how you can find the number of the group homomorphism from the Q8 to this and K4 to Q8. Similarly, Sn to K4, Sn to Q8, An to K4 and An to Q8. Q8 to Q4 is my 16, while the converse is my 4. Sn to K4 is 4 whenever n is my greater than 3 or equal to 3. Sn to Q4 is my 2 whenever n is greater than equal to 3. While in both the cases An is alternating group, it is always my 1 and 1. Now, the number of the non-isomorphic, remember that. Is it given that abelian group? Is it given in the abelian group? No. So now, what is the shortcut tricks? How you can define the number of the non-isomorphic group? Number of the non-isomorphic group. First of all, very simple. I will tell you firstly the shortcut tricks. If number of the if order of the G is my P into Q, where P and Q are prime, fine, such that P is less than of the Q, then the number of the non-isomorphic groups, it will be either 1 or 2. 1 if this G is my cyclic, or there is no need of them. You can simply write that if P doesn't divides Q minus 1 and if P divides Q minus 1, then the number of the non-isomorphic group is my 1 if P doesn't divides Q minus 1 and if P divides Q minus 1, it is my 2. So let me check how you can define that 122. 2 into 61. So clearly say 2 is less than of 61. So P will be my 2, Q will be my 61. Fine. Now clearly say 2 divides 61 minus 1. Yes, 2 divides 60. So that means this condition satisfied. Number of the group homomorphisms are my 2 is the right answer. Fine. So clearly say 61 and 4 can never be possible. So the right answer of this problem is A is my right. Okay, let G is a non-abelian group. Is a non-abelian group. Then can be, the order can be. First of all, very simple. What is the shortcut tricks for you? Whenever order of the G is my P square, then the group is always abelian. Fine. If G is my cyclic, this implies G is my abelian. Fine. So firstly, we will how you can check about the cyclic. Again, if order of the G is my P into Q and P is less than of the Q, where P and Q are my prime numbers. If P doesn't divide Q minus 1, this implies the group is cyclic. So look at that first number, 25 is a P square where P is pi prime. So that means this is my abelian, but we need a non-abelian. So this option is cancelled. 55, 5 into 11, P into Q satisfied, but 5 divides Q minus 1. So that means it may be cyclic or may not be. Fine. So that means it may be cyclic, that means it may be abelian or may not be. Fine. So now you can see the option is can be. So that means yes, it can be non-abelian. 125. 125 is my P cube. So whenever it's a P cube, then it is always be a non-abelian. So yes, it's a non-abelian. 35. 5 into 7. So clearly say 5 doesn't divide 6. So that means this group is my cyclic. Once it's a cyclic, this means this is my always abelian, but we need a not abelian. So the right answer is B and C are my correct answer of this problem. I hope you can support my videos too by liking and commenting on this video, because I uploaded this video based on your several requests. Otherwise, I am not interested to upload on the group theory problems. But because you have requested me several times, so I try my best to explain you the problems related to the group theory. So that's why I'm asking you. I hope you can support my videos by liking and sharing, comment on this video. Let G is the group of order 77. Then the center of the G is isomorphic to what? Again, a very simple. This is isomorphic. First of all, we can see whether it's a cyclic or not. 2, 7 into 11. Clearly says 7 doesn't divide 11 minus 1, 10. So that means this group is my cyclic. Once the group is cyclic, what does it mean? The center of the cyclic group is isomorphic to the group itself. So that means group of, or you can say the center of the cyclic is isomorphic to the Z of order of the G. Fine. So that means what is the order of the G? 77. So this will order to the 77. So the right answer of this problem is D is my right answer. We all know that if G is my cyclic, fine, then the center of the group is isomorphism to the Z of the order of the group. The number of the group homomorphisms from the alternating group A5 to S4. Fine. Now you can see, if you look about this concept, this is the AN to K4, but not from the S4. Fine. Now look at this one. If you look about the definition, I'm not talking about any of the A5 in my shortcut tricks. Fine. But that's a very simple. First of all, A5 is my simple group. We all know that AN is a simple whenever n is greater than or equal to 5. So then by that, because it's a group homomorphism, so that means A5 over kernel of the F is isomorphic to the S4. Fine. Now if A5 is my simple group, how many normal subgroups are there? Either the identity or A5 itself. Fine. Now you have the two cases. But what will happen if kernel of the F is identity? Fine. Is it possible? No. Because if kernel of the F is identity, that means the F is 1, 1. But that is not possible. Why? Because how you can check about the 1, 1? What is the order of the A5? A5 is 5 factorial over 2. That is the 120 over 260. And order of the S4 is my 4 factorial, 24. Fine. So that means you have the one group of order 60 to one group of order 24. So clearly say 60 doesn't divide 24. So that means it is not 1 1. Fine. Or second way is, we all know when the function f from a to b is 1 1. If this is a 1 1, then the order of the a must be less than or equal to order of b. But you can see the order is 60 is greater than of this, so that means this is not possible. That means the function is not 1 1. If it is not 1 1, that means kernel of f is not identity. So the only remaining thing is my a5. That means you have kernel of the f is a5. That means you will get only trivial homomorphisms. Fine. So that means the only homomorphism is my 1 is the right. This is happening only because A5 is my simple. If any of the other A which is not a simple, then you have to find all those normal subgroups and look at these options. How many generators a cyclic group? Again, a very simple. What is the shortcut tricks for the number of the generators? Number of the generator of the group G. Make sure G must be cyclic. Fine. Then it will be my phi of n, where n is order of the group. If your group is cyclic, remember, if your group is cyclic, then you can find the number of the generator as phi of n. It is given that the 36 is my cyclic group. So what is the group of number of the generator? I can write is a prime factorization. Is a 6 square, that's a 2 raised power 2, 3 raised power 2. So it is my 4. Fine. What is the, as I told you, this will be my n over 2 if n is my 2 raised to power k4. So for this case, it is my 4 by 2. And for 3 raised to power 2, I can write this as 1 minus 1 over 3. So 2 into 9 into 2 over 3. So that is 4 into 2. That is 4 into 3, 12. B is my right answer of this problem. Next concept. Now, so far we have defined how you can check about the homomorphisms, how you can check about the number of the isomorphisms, fine, how you can define the how many up to the isomorphism abelian groups, and how you can check about the number of the non-isomorphic group. This is we have defined so far. Now, if you are looking like this photo, if you are searching for how you can find the number of the group automorphisms. What is the automorphism is? Defined from the G to G. Fine, that's the same to same. Then how you can count the number of the group automorphisms. Once you know how you can count the homomorphisms, once you know how you can count the isomorphism, we can define the group automorphism. First of all, automorphism of the is always be an abelian group. Fine. So then you can define the automorphism is isomorphic to the U of n. Then how you can define the number of the automorphism of Sn as 6. So definitely it is when n is not equal to 6. D of n, dihedral group, Z of n, this is the infinite group. Very simple approach. If you look about like it's a very difficult, like if you are one of them, if you think about that, it's a very difficult. I will tell you again the short way. The number of the automorphisms are always n factorial. Make sure n must be greater than equal to 3 and n is not equal to 6. On the other hand, how you can define the S6? It will be twice of n factorial. Fine. Or in this case, n will be my 6, so twice of the 6 factorial. How you can define the D of n? It is dihedral group, that is the n into phi of n. Again, the phi is my Euler function. If you are the finite group of the order Z of n, then you can define the number of the automorphism as D of n. If you have the infinite groups, Z is my infinite group, then the number of the automorphisms, group of automorphisms are my 2. Look at that. And number of the inner automorphism from the Sn is n factorial, where n must be greater than 2, or you can say n must be greater than equal to 3. Look at this example. F is the mapping from Z6 to Z6. Fine. How many automorphisms are there? Look at that. How many automorphisms for the Zn? Phi of n. So the right answer of this problem is phi of 6. So phi of 6 I can written as 2 into 3. So that means 2 into 3, 1 minus 1 over 2, 1 minus 1 over 2. That's a 6 into 1 over 2 into 2 over 3. The right answer of this problem is 2 is the right answer. If somebody will ask you find the number of the group homomorphisms, how many group homomorphisms, because they are finite to finite, then it's a GCD of 6 comma 6, that will be 6. Then in that case this will be the right answer. Now let G is a cyclic group of order 24. Then the number of the group isomorphisms of G, any group of order 24, fine, it is given to you. Then you have to define the mapping from G to G. Then the total number of the group isomorphism. Number of the group isomorphism. What I told you, this is nothing but, because it is my finite group of order 24. So that means it is nothing but my phi of 24. Phi of 24 means 8 into 3. So what is the right answer of this? So it's a 2 raised to power 1 minus 1 over 2. Sorry, 2 raised to power 8 into 3. So 8 into 3. So that will be 2 raised to power 3, 1 minus 1 over first prime, 1 minus second prime. So it's a 24 is 1 over 2 is 2 over 3. 6 into 4. So that will be 8 is my right answer of this problem. You can see that a very simple approach I have given you about the isomorphism, group homomorphisms, and the abelian group. I hope you can learn many shortcut tricks through this video. I hope you can like, share, and comment on this. Best of luck, students. Happy luck.